Hello students, welcome to the class. So today we will see the theory part 10 of the chapter Thermodynamics, in which we will cover from 5.6 to 5.7. So we started the section 5.6. Some part of it is still left. So I have left it intentionally to discuss this today along with the Gibbs energy part, right? So this is the disclaimer. Now if I talk about today's objective. So our today's objective would be to study about the Gibbs energy and spontaneity. Then we will try to explain the Gibbs energy change in terms of mathematical formulation. If I talk about the specific topic according to the NCERT, then the first would be spontaneity, in which we will cover Gibbs energy and spontaneity. So we've already dealt with entropy and spontaneity. What is the relation between the spontaneous process and how do we decide it with the help of entropy? And we have seen that we were facing a problem, right? So we have seen that in case of entropy, we have to know it for the whole universe, which is near to impossible. Therefore, it was difficult for us to decide the spontaneity with entropy as a state function. So here we will devise a new state function known as Gibbs free energy. At last, we will try to discuss it along with the equilibrium. So Gibbs free energy has some aspects related to the equilibrium. Although you are not introduced to this concept, I will try to explain in a compact way so that you can actually get the idea what is the relation between the equilibrium and the thermodynamics. So let us start our discussion. So first, let us try to relate the Gibbs energy and the spontaneity. Now, if I talk about the Gibbs energy, then it is a fundamental thermodynamic potential, and its most important part is it helps us to predict the spontaneity of a process, right? So this is the most important and fundamental reason for developing the state function known as Gibbs free energy. We tried to use the enthalpy, we failed there. We tried to use the entropy, we also failed there because of some limitations. Now we are moving on to a new Gibbs free known as Gibbs free energy to decide the spontaneity. So total entropy change is the one which is deciding the process spontaneity. So if in some way we can calculate this total entropy, then we can decide the spontaneity. And I will derive the Gibbs free energy of the system in terms of the total entropy so that you can calculate it. Now, the problem is that with the total entropy, that most of the cases, the universe with which the system is interacting is a very large one, and to see the heat exchange between those is very difficult, right? But two things are there which is helping us to decide the spontaneity. We know it for sure that although enthalpy is not playing the whole role here, but still we know that for exothermic reaction, the reactions are spontaneous. The second thing is your randomness. So two things. First is the heat exchange, and second is the what? The randomness. These two things are the one which are deciding our spontaneity. So we will incorporate both of these aspects of spontaneity in the Gibbs free energy part. Now, Gibbs free energy is an extensive property as well as it is a state function. And the thermodynamic function which is used to dictate this Gibbs free energy can be written as G is equals to H minus Ts. Now you can see clearly in the equation that we have included enthalpy as well as entropy. So we are dealing with the heat change and our randomness to study the spontaneity, which is there in terms of Gibbs free energy. Now, what should be the value of Gibbs free energy and what are the procedures that we will follow to apply the same? We will look on to it. So first of all, we will try to calculate the change in Gibbs free energy. The formula that you have seen right now, it was for the actual value, and to calculate the actual value of Gibbs free energy, we need the actual entropy and we need the actual enthalpy, which is impossible. And the good part is that our importance is for the change only, and we don't have to consider the actual value. So that's a good news. Now moving on to the change of Gibbs free energy for the system, we can write it as delta G is equals to delta H system minus T delta S system. Then we have S system delta T. So basically it's a type of differentiation if you see. So we are keeping in the first part T constant and differentiating the entropy. In the second part we are keeping the entropy constant and we are differentiating the temperature. But here the differentiation is related to a large change. Okay, so we are representing it with the help of delta. So upon applying it for the greater change, we got this equation. Now next thing is that we are keeping the temperature constant, suppose. So therefore delta T will be equals to 0, and hence we got our final useful equation for the Gibbs free energy, which is delta G system is equals to delta H system minus T delta S system. Next, here the SYS that you are seeing constantly is subscribing the system. Okay, and if you want, then you can drop this term also, and finally the equation can be written as delta G is equals to delta H minus T delta S. So this equation is the one which you will surely notice in most of the textbooks, and this is NCERT equation 5.21. Okay, now we will look at the different aspects of this reaction. So this is our equation. Now what are the terminologies that we are seeing here? So let us just write them in short so we can use our equation in a much more better manner. So delta G is equals to net energy available to do the useful work, which is Gibbs free energy. Then next is delta H, which is enthalpy change. Then after that we have T delta S. So this is the energy which is not available to do the useful work, right? Okay, and what about delta G? So delta G will have a unit of joule, and it's obvious. So if you have studied the, I would say, the unit analysis, then you must have seen there, since delta G and delta H are present at the same algebraic term, so they will have the same unit. And you know enthalpy is a kind of energy, so it has an unit of joule. So delta G will also have a unit of joule. Got it? Now moving on further. Next we have relationship to spontaneity. Whose relationship? Of course, your enthalpy relationship. Enthalpy and entropy relationship. Okay, now for this table that you are seeing right now, we will go through a series of derivations, but for now just take it for a start point, and this is very important. Okay, so if you want to decide the spontaneity of a given process, then you just have to calculate the Gibbs free energy change, okay, for the system and not for the overall surrounding. And this is the upper hand that we got with the help of Gibbs free energy. So if your change in Gibbs free energy is negative, therefore your process will be spontaneous. If it is greater than 0, which is positive, it will be non-spontaneous. And the third and the most important one, if it is equals to 0, means the Gibbs free energy is not changing at all. That means your system has already attained the equilibrium, and we will look onto this with a separate section. Now let us try to validate this 3 equation with a derivation. We know from our previous discussion that total entropy change can be written as the entropy change of the system plus the entropy change of the surrounding. Then if the system is in thermal equilibrium with the surrounding, and we have seen that we were keeping the temperature constant, then what can we write? The temperature of the system and surrounding will be same. Okay, and whatever the increase in enthalpy of the surrounding that we are observing, that same amount of enthalpy will be decreased in the system. So basically what amount of heat is lost by the surrounding, that amount of heat is gained by the system, and the vice versa is also true. If this is true, what can we calculate for the entropy change of the surrounding? We can write it as delta S surrounding is equals to delta H surrounding by T, and that will be negative of the enthalpy change for the system. I have told you right now, right? So we are doing this process in such a way that the heat that is lost by the system will be gained by the surrounding, and the heat that is gained by the system will be lost by the surrounding. I hope this point is clear to you. Now you can relate it. So how are we writing it? Delta S is equals to delta H by T. So here we are keeping the pressure also constant. Why we are keeping the pressure constant? Because most of the reactions that we carry out, we keep it in an open container, and therefore the pressure is equals to the atmospheric pressure. And if the pressure is constant, then we can replace the Q reversible with the enthalpy, and that we have done that same thing. Now for positive, we will have plus Q surrounding, therefore we can write it as enthalpy change for surrounding. And for the opposite case, which is system, we can write it as minus Q reversible system, therefore minus enthalpy change for the system. So what do you know about the first term? How can we write this? We have seen it earlier that delta G is equals to delta H minus T delta S, right? We have seen this. And we have also seen an equation that delta S system is equals to delta H by T. So we will simply replace this by delta S system. Is this clear to you? Is this point clear to you? So what we have done, we have just substituted it. We have substituted the value of delta S surrounding with the upward equation that we are seeing, okay, and nothing else. Okay, if this is clear, let us move forward. So what equation did we get? We get delta S total is equals to delta S system plus, then in a bracket we have the negative of enthalpy change for the system divided by temperature. If this is true, we can multiply the whole equation by T. Then what we will get? T delta S total, T delta S system minus enthalpy change for the system. Now what can be said for the T delta S total? We know that the spontaneity criteria puts us in the situation so that the total inentropy change should be greater than 0. Okay, that means this delta S total will be greater than 0. Okay, this is the first part. And the temperature can never be negative because we always use the Kelvin scale for representing the temperature, and Kelvin scale in no term can go to the negative part. So that is nearly impossible to attain. Okay, since both of the terms are now positive, what we can say? We can say that your whole T delta S system minus delta H system will be greater than 0. If we just rearrange this equation, we can write it as delta H system minus T delta S system is less than 0. Simple. We have just rearranged this equation and we finally got our situation in which we are for which we are searching for. Can we relate it with a simple term? Yes, we can do it. We know that this change in enthalpy minus temperature multiplied by change in inentropy can be written as the change in Gibbs free energy. Therefore, we can say finally that if you want your process to be spontaneous, your Gibbs free energy change should be negative. Hence, we finally moved to our very important conclusion that for spontaneity, the delta G should be less than 0. I guess this part is clear to you, and this derivation part also. Okay, if I talk about the derivation part, it is not that much important, but still you must know it because it gives you a clarification that why we are doing it so. Okay, and the second thing I would say is you should remember this relation, that for what condition we have a spontaneous process and for what condition we have a non-spontaneous process, and the third one is for the equilibrium. Okay, if this is good, let us move on to the effect of temperature and spontaneity. So we have dealt it with the help of the Gibbs free energy change equation. So what was that equation? Delta G is equals to delta H minus T delta S. So two things are one which were deciding the sign of the delta G. Why? Because temperature will be always positive. Okay, so we can't change it. It's a constant one. We can talk about the enthalpy change and the inentropy. Okay, so we will take different cases. The first case is the delta H is greater than 0 and the delta S is also greater than 0. Then what we can say? If you look at the equation, we can say that the reaction can be only spontaneous when the T delta S is greater than delta H. How we are saying it? See here, if you look at the equation, if your delta H is greater than 0, means this term is greater than 0. Okay, delta H system is greater than 0. Now, if your delta S is greater than 0, then your whole product will be greater than 0, but we are having a negative sign in between. Now, if your T delta S is suppose greater, then what it will result in? It will result in an overall negative value of delta G. You can just simply put values here and check it. Suppose in the first case, we take delta H value as 5 and T delta S value as 6. So 5 minus 6 will be minus 1. That means a non-spontaneous process because delta G is positive here, negative here. A spontaneous process, sorry. A spontaneous process. Next case, what we can take, delta H as 8 and T delta S as 2. In this case, you will get a positive value. Therefore, your process will be non-spontaneous. So what can be deduced from here? If both of your enthalpy change and entropy change are greater than 0, then your T delta S should be greater than enthalpy change. Got it? Now, what are the possibilities? First possibility is that if your delta S is small, suppose if you want to have a greater value of T delta S, two possibilities are there. Either your temperature is high or your enthalpy change is high. So in the first case, we are saying that your entropy change is low. So to keep the spontaneous process, we have to increase the temperature. Next, if the delta S is already large, then we can take a lower temperature. In that case also, your entropy will be, your system will be going under a spontaneous process. Okay, so this delta S is large enough so that the delta H system will be less than the T delta S. So that is the basic criteria. We have to follow this. So this is the reason we do some reactions at higher temperature and some reactions at lower temperature. You can easily conclude that situation here, right? So if the delta S is small, we require a large temperature. If delta S is large, we require a small temperature. Okay, so now we have seen it for only, we have only seen it for the requirement of high temperature. We will see it for the low temperature requirement also. So why in some cases we require low temperature? Let's see on to it. Okay, so we have a table here to justify all of these situations. So first is, if you are having a delta H negative and a delta S positive, then in that case, you will always get a negative, what? Negative Gibbs free energy change. So in that case, reaction will be spontaneous at all temperature. What you can do is simply take that equation and take different values, right? And you will get your thing. Second case, if both enthalpy change and entropy change are negative, then we have to keep a lower temperature to keep the process spontaneous. Third one is what? Third one is, if one is negative and the other one is also negative, and if we keep the temperature also high, then in that case, the reaction becomes non-spontaneous. So what we can conclude from these 2 points, that in reactions where the reaction is exothermic, first of all, and the system is also not undergoing a greater entropy change, okay, it is getting a negative entropy change, and then in that case, you should do the reaction at lower temperature, and you can deduce the same with the help of what? With the help of your equation. Just try it by yourself. What is the third case? Third case is that you take both the values as positive. Okay, if you take both the values as positive, then the reaction will be non-spontaneous at lower temperature and highly spontaneous at high temperature. And the last case, in which the enthalpy change is positive and the entropy change is negative, in that case, all temperature will favor the non-spontaneous process, or I would say there will be a non-spontaneous reaction if we have an enthalpy change as positive and entropy change as negative. Again, I am telling it again and again. Just try to get this points with the help of a example, okay? Or you can take values, try to increase the temperature, keep different values in different I would say negative and positive, and try to deduce that whether this results are true or not. Okay, so I'm leaving this task up to you. Next, we will move on to uses of Gibbs free energy. So delta G can be used for several things, and it's the most important part. We have seen it, that it is helping us to decide the spontaneity, as well as it is helping us to decide the temperature at which the reaction will be spontaneous. Okay, so first thing what we got the prediction of spontaneity. Then we got that how much energy is available for the reaction to be carried out. Then third thing what we got that at what temperature the reaction will be favorable. Then what about Gibbs free energy and reversible reaction? So this is very important. Okay, so this relation will be also encountered in the next chapter, which is equilibrium. So if a system is always in perfect equilibrium with the surrounding, is a truly reversible process. Okay, so it is the basic requirement of the reversible process. We know it very well. Now, if you want to keep the reversible system, okay, if you want to keep the reversible system at equilibrium, then you need to keep the Gibbs free energy at minimum value. How? Suppose you have a system and the system has a minimum value of 2. Okay. So it can have minimum value of Gibbs free energy as 2. Now, what other values can it have? It can have 2.1, 2.2, 2.3, 4, 5, 10, anything. But whenever you will try to calculate the Gibbs free energy change, then what you will observe that if you're going from the state where the Gibbs free energy is 2 to a state where the Gibbs free energy is even higher, then in that case, what will happen? You will always get a positive value for the Gibbs free energy change. Means the system will try to remain in that state only where the Gibbs free energy is minimum. So this is very, very important. Okay. If you want to get all of these points, my suggestion would be try to solve as much as numerical as you can. Okay. If you have a problem, post it on our forum. And I hope you will get this thing. It's very, very easy. These are just simple algebraic calculations. Okay. Now, let us try to deduce a relationship between the equilibrium and the delta G, or the standard Gibbs free energy and the equilibrium constant. Now, there is a previous relation which tells us that the Gibbs free energy change for a given reaction is equals to the Gibbs free energy at the standard condition plus RT ln Q. Now, we are not aware about this Q and all. We'll talk about this, but we will only tell you the equation right now, so that if you see the equation in the further chapter, you are not confused about it. So basically, at equilibrium, if I talk about the values, so delta G becomes 0, means then Gibbs free energy change becomes 0. We have seen it. Then the next thing is that Q is equals to K. So Q is basically a value which we get at non-equilibrium state, and K is a value which we get at equilibrium state. We will talk about it. How do we get it? So if K is a value at equilibrium state, what we can say? We can simply substitute this thing and get our standard Gibbs free energy change in terms of equilibrium constant, which is minus 2.303 log K. So we have just replaced ln K with log K 2.303, right? Now this standard Gibbs free energy change is also equals to delta H naught minus T delta S. So we have done the same. Now next is the effect of enthalpy and entropy on K. We have seen the effect of Gibbs energy. Now let us talk in terms of enthalpy and entropy, which is delta RH naught and delta RS naught. First is the impact of enthalpy. Now, if your reaction is endothermic, which is large and positive, okay, then your K value will be less than 1. You can see it from here. Okay, if you have a greater value of delta H, right, then what you will get? You will get a minus RT ln K is equals to positive. Okay, you will get this thing. That means RT ln K is equals to negative, or K is less than 1. Similarly, if you are having an exothermic reaction, which means the value of enthalpy change is negative and it is large, then in that case you will get a greater value of K. Now why I am saying it? See, if you just take a greater value of delta H naught, that means minus RT ln K is a greater value, right? Or you can also say RT ln K is now a smaller value because there is a negative sign here, right? You got it? Basically, so RT ln K, if you are getting a smaller value, that means ln K is also a smaller one and K is also a smaller one. Similarly, if this value is lesser, that means you will get your overall value as negative. Negative will get cancelled out. So you will get a greater RT ln K value. That means your K value will be greater. Now let us try to understand the same with the help of entropy. If I talk in terms of entropy, then if you take a positive term, right? If you take a positive entropy, then what will be its effect? So it will result in a negative term, right? Now more negative is this term, more spontaneous will be your process. And second thing, if it is a negative term, then this T delta S will be positive and your process will be less spontaneous. Now what about K? What happens to K? So if you are getting a positive entropy change, then in that case, the product is favored, or you can also say K is greater than 1. Similarly, if your entropy change is negative, then in that case, K is less than 1. Now, is this discussion been already done? Yes, you have done this discussion earlier. We have told you that if your system is moving to a higher inentropy, that means your system will do more favor to the product. And we can see the same here. So inentropy change is positive, means larger value of K, or you can say greater amount of product form. And if your reaction is exothermic, then in that case also your K is greater than 1. Now, what can be the practical application of this delta G naught and K relationship? We got this equation right. We have seen this delta G naught, which is the Gibbs free energy change at standard temperature, is equals to negative of RT ln K, where K is the equilibrium constant. Now you can predict the K from H naught and S naught. If the enthalpy estimation of equilibrium constant is done at various temperature, then the value of optimizing product is yield. Okay. So if you keep delta H naught much and more negative, you will get more and more product. Similarly, if you keep your delta S more and more positive, you will get more and more product. Again, both are same, but in different terminologies. And what is the second thing? We can calculate the Gibbs free energy change at standard condition from the equilibrium constant, from our equation, which is delta G naught is equals to minus RT ln K. And K can be easily deduced from the experimental result. Okay, so this is the basic use of this equation. It is very difficult to determine the enthalpy change and all of these in an experiment, but it is very easy to determine the equilibrium constant. Okay, we'll talk about it and you will easily notice that yes, this thing is easy. If you got your K, then you can easily determine your enthalpy change without getting into the reactions heat process. I guess this part is clear to you. Now let us try to do a question on the same. Okay, so I'm leaving this question on to you. So this easy one. What you have to do? Delta G naught value is to be calculated and Kp value is already given. It is 2.47 10 to the power minus 29. Okay, just try to solve it by yourself. Meanwhile, I will move further. Here is the next question. So this is also a homework for you. You have to find out the value of equilibrium constant. The reaction is given, and the standard Gibbs free energy change is also mentioned at a given temperature, which is minus 13.6 kilojoule per mole, and it is at 298 Kelvin. Okay, so let me do it for you. But before that, you will try it by yourself. So you have some time to solve it. Your time starts now. Okay, 5 more seconds. Okay, so time is up. Let's see how we can solve it. So what is given in the question? We are given with the Gibbs free energy change, and you just have to find the equilibrium constant. The temperature is also mentioned, and you know the equation as well. So the equation is delta G naught is equals to RT ln K, or delta G naught is equals to minus RT ln K, and delta G naught is equals to minus RT log K multiplied by 2.303. So we have just rearranged it. Then we put the values here, and after calculating this, we got it as 2.38. Okay. Now what we do? We got this value of log K. We will take the anti-log. Therefore, this value will be 2.4 into 10 to the power 2. So this is your final answer. Thank you for attending the session. I hope you enjoyed it.